Hi, welcome to Chump, a 4-bit TTL processor. This is the first stage, which consists of the clock and the counter. I'm going to be mainly focusing on the program counter, as we've used the 555 chips before, but here's a quick overview of the clock circuit first. So there are 3 555 timers. The first here is an A-stable mode, which gives us a square wave. The frequency of the square wave can be controlled using this potentiometer, and it can be visualized using this LED. The next is in monostable mode, which gives us a rising edge whenever this button is pressed. It essentially acts as a debouncing circuit. Finally, this 555 is in bistable mode, which gives us either a high or a low, depending on the position of this slide switch. The outputs of the 3 555s are then fed through these 2 NAND chips using combinational logic, which allows us to select between either a manual or an automatic pulse that advances the program counter. In manual mode, one press of this button will cycle at 1 clock cycle. This button can halt the counter by preventing the clock signal from being passed through, and this button will cause the program counter to go to the binary value inputted on this dip rocker switch. This feature allows us to simulate a branching instruction, which will eventually become important as it allows us to go to specific lines in our program, and it'll be influenced by the address buffer and control ROM. Okay, so before we get into how any of it actually works, I think it's more important to have a big picture of how where this fits into the final Chump build. So right now we're here, PC, the program counter, and each one of these bold lines symbolizes a bus, which, since it's a 4-bit computer, is 4 wires that allows the different sections of the processor to communicate with one another. So this little triangle symbolizes the clock. The clock synchronizes all the components on each rising edge of the clock signal. That's when each component advances. So any component that's influenced by the clock has one of these triangles. And so as for the program counter, what it does, it basically determines which line of the program the processor is on. So it's nothing more really than just an address in the program ROM, and the address ranges from 0 to 15. The address buffer can also influence it when the load pin is pulled low, which was the branching instruction we saw earlier. So now that we understand where this fits in, let's get to how the program counter actually counts. So here's somewhat of a deep dive into how the actual program counter chip works. The basic circuit which this chip makes use of is called the D flip-flop, which is outlined here. Conceptually, it's a pretty easy device to understand. It basically stores the logic level presented on its D pin on the rising input of the clock. So if it receives a 0, it'll store a 0. If it receives a 1, it'll store a 1. And then the Q bar output is always just the opposite of the Q output. So in this configuration, since the Q bar output is the opposite of the Q output, that means that whatever's on Q currently is whatever was previously on D. So then when the clock receives a rising signal, a rising edge, the Q bar output, which is whatever a Q is not, will be stored. So this means that on every rising edge of the clock signal, the Q output will toggle. So it'll effectively divide the clock signal by 2, and it will toggle the Q output on every rising edge of the clock signal. So to understand how the program counter chip works, here's the internal schematic of all its logic directly from its datasheet. So it looks like a lot, but as we can see, there are 4 D flip-flops, and they're all interconnected using combinational logic. But most importantly, what we can see is all the clocks are linked together, which means they have a common clock source, which comes from our 555. So here's a quick breakdown of the schematic. Essentially, the first flip-flop, which controls QA, is wired exactly as it was in the previous example. The Q bar output is directly attached to the D input. And so this divides the clock signal by 2, as we know. And then the Q output is then attached through a series of logic gates in conjunction with Q bar of B, and basically it passes the value of Q bar when QA goes from 1 to 0. So on the falling edge of QA, it allows this value of QB to pass through. So it toggles this flip-flop every time there's a falling edge on this. So then it divides this by 2, so it ends up having a quarter the frequency of the clock cycle. Then each flip-flop kind of works in the same fashion as that. For flip-flop C, it passes the value of Q bar C, this one, when QB goes from 1 to 0, so a falling edge. So then it divides this flip-flop by 2, so it runs at 1/8 the clock frequency. Finally, flip-flop D passes the value of Q bar D, the inverted Q, when QC goes from 1 to 0. So on the falling edge of this flip-flop, it toggles the value of flip-flop D. So it runs at half the frequency of flip-flop C, in other words, 1/16 of the clock signal. And then the result of this is what I like to call a simulated binary counter, because all a binary counter really is frequency division. The least significant bit toggles at half the rate of the clock frequency, then the second least significant at a quarter, then an 8, and so on, in this case up to 1/16. So just going back to our binary counter, if we just pay attention to the rightmost bit, every time there's a rising edge of the clock signal, this toggles. So rising edge, it turns off, rising edge, it turns on, rising edge, it turns off, rising edge, it turns on. So that's how the program counter and clock circuit works. Thank you so much for watching, and we'll see you in the next stage of Chump.